Imagine for a second a highly experienced doctor examining a really complex medical scan. When they finally make a diagnosis, they aren't just staring at the pixels in front of them and making some magical, educated guess. They're actively cross-referencing that specific patient's scan with thousands of historical cases they've seen throughout their entire career. It's a deeply evidence-based, highly comparative process. Now contrast that with how most of our current medical AI works. Today's AI usually just looks at a scan and spits out a black box prediction. It says sick or healthy, but it absolutely cannot show you its work. This massive gap in reasoning is exactly what we're exploring today. Welcome to this explainer, where we are going to dive deep into a fascinating new research paper introducing EviScreen. It's a groundbreaking architecture designed to finally teach medical AI to think and actually justify its answers, just like a human doctor.
Here's our roadmap for this explainer. We'll start with the medical AI black box, then introduce evidential reasoning, break down how EviScreen actually works, look at the proof in the data, and finally discuss the future of AI healthcare.
All right, part 1, the medical AI black box and the critical lack of transparency. Right now, we basically train AI to screen for diseases in two main ways, and honestly, both of them fall short. First, there's deviation-based prediction. This is where the AI only learns what a perfectly healthy, normal case looks like. If it sees anything that deviates from that baseline, it flags it. The problem there? It completely ignores all the incredibly valuable data about what specific diseases actually look like. Then, on the flip side, we have direct prediction. This AI trains on both healthy and sick patients, which, sounds a lot better, right? But it operates as a total black box. When it makes a prediction, the absolute best it can do to explain itself is generate what's called a post hoc saliency map. Essentially, that's just a glowing heat map layered over the image.
But here's the thing. The crucial missing piece in these current models is case-based evidence explaining exactly why a region appears pathological. A heat map might highlight a blurry spot on a lung or a retina, sure, but it doesn't give the clinician any real, fundamental reasoning. It can't say, hey, I'm flagging this spot because it looks exactly like these 3 confirmed cases of melanoma from last year. Without that historical evidence to back up its claims, doctors are literally forced to blindly trust a machine. And in medicine, that is a massive liability. We desperately need AI that brings the receipts.
Which brings us to part 2. Enter evidential reasoning, a real paradigm shift.
EviScreen introduces a vital, totally game-changing concept called retrospection interpretability. So what does that mean? It's the ability of an AI to trace a single decision directly back to historical, normal, and pathological cases. Think about that for a second. It completely mirrors a seasoned physician mentally flipping through past patients to confirm a tricky diagnosis. Instead of just giving a binary prediction and a generic fuzzy heat map, EviScreen actually pulls up the exact historical image patches it used to make its decision, laying them all out side by side for the doctor to review. It brings a completely new, desperately needed level of accountability to the table.
Okay, section 3. Let's get into the engine room and see how EviScreen actually works.
When you look at the blueprint of this framework, you can see exactly how the architecture evolves. You've got the older deviation and direct prediction methods we just talked about, but the real magic is evidential reasoning. When EviScreen gets a current case, it doesn't just pass it through some generic neural network to magically guess an answer. Instead, it extracts regional features and uses them as super-specific queries to retrieve evidence from what the researchers call dual knowledge banks. It is actively hunting down actual image patches of historical evidence to generate both that retrospection interpretability and incredibly precise abnormality maps. It's just a totally different workflow. So, let's break down that complex architecture into 2 really clear sequential stages so we understand exactly how this engine runs. Step 1 is the dual knowledge bank construction. Basically, before the AI can screen anyone, it needs to build its internal library of knowledge from a vast training set of scans. Then, step 2 is the actual disease screening via evidential reasoning, where it puts that freshly built, massive library to work on a brand new patient.
To understand step 1, think about typical retinal scans. You have healthy, normal eyes, and then you have scans with clear pathological anomalies, things like lesions or exudates. EviScreen uses a foundation model to extract intermediate regional features, essentially breaking these incredibly high-resolution images down into tiny, mathematically understandable patches. It then subsamples these features to create 2 highly compact, distinct banks, a normal knowledge bank and a pathological knowledge bank. It's literally building 2 massive, entirely distinct reference encyclopedias, one for health and one for disease, from thousands of historical cases. Now for step 2. When a brand new patient scan comes in, the model performs what's called evidence awareness. It takes a tiny patch of the new scan and actively compares it against those two vast banks of historical data it just built. It uses a mechanism called cross-attention to retrieve the k-nearest neighbors. Basically, it's aligning the incoming patient scan with retrieved historical evidence in real time. It's actively asking the critical question: does this specific patch of tissue look more like the healthy encyclopedia or the pathological encyclopedia?
And because it evaluates the precise mathematical distance between the new scan and both sets of historical data, a process called contrastive retrieval, it completely avoids generating those vague, fuzzy heat maps of older models. Instead, EviScreen produces a highly focused abnormality map. It pinpoints exactly where the problem lies with incredible localization interpretability. Why? Because it has definitive mathematical proof of exactly which region deviates toward known diseases and which region aligns perfectly with healthy tissue.
Moving right along to Section 4, the proof in the data. The researchers didn't just theorize this. They put it to the test across multiple, highly complex medical datasets spanning ophthalmology, radiology, and dermatology, specifically the JSEC, CheckSpay, and Derm12 datasets. They compared EviScreen against older deviation-based models like PatchCore as well as direct foundation models. And EviScreen consistently achieved the highest scores, particularly in a key metric called specificity at clinical level recall. Let me translate what that hard data practically means for a doctor. Recall means finding the sick patients, which obviously is critical. But specificity means correctly identifying the healthy patients so you don't raise false alarms. EviScreen manages to expertly catch the sick patients while dramatically reducing the number of false alarms compared to older AI models. That is an absolutely incredible clinical achievement that directly impacts patient anxiety and saves hospital resources.
And honestly, the results get even wilder when we look at CSR, or clearer separation. This metric measures the gap between the AI's confidence in predicting a negative case versus a positive case. You want this gap to be as wide as humanly possible so there's absolutely zero ambiguity. EviScreen just smashed the competition here, surpassing the runner-up methods by margins of 9%, 11.2%, 23%, and on one dataset, an astonishing 37.5% margin. I mean, in the world of machine learning, beating a state-of-the-art model by nearly 40% is practically unheard of. It creates a much wider, clearer gap between sick and healthy predictions, basically eliminating that dangerous, mushy middle ground.
Now you might be wondering, okay, cross-referencing a brand new scan against millions of historical patches, that must take forever to run, right? Well, the actual deployment statistic is 0.6 seconds. That is quite literally less time than it takes to blink. Yet it's enough time for EviScreen to retrieve evidence from a massive radiology bank containing over 1 million complex vectors.
To put that into perspective, a 4 GB radiology memory footprint can be thoroughly searched in just over half a second. This drives home a really crucial practical point for hospital IT administrators and doctors alike. This system isn't just some academic exercise living on a supercomputer in a lab. It is incredibly lightweight, blindingly fast, fully scalable, and capable of being deployed right now in real hospital environments without causing massive computational bottlenecks.
Finally, Section 5. What does this mean for the future of AI in healthcare?
The overarching impact of EviScreen really boils down to one word: trust. By providing transparent reasoning pathways, clinicians no longer have to blindly trust a machine. They can independently review the exact historical evidence the AI used to make its call. This combination of highly accurate predictions and clear, localized evidence drastically reduces clinician workload, cutting down the frustrating hours spent second-guessing black box models. And because those dual knowledge banks are scalable, hospitals can continually update the AI's memory with new, diverse cases without having to entirely retrain the complex system from scratch.
It's just a massive leap forward from the days of simple deviation maps and vague heat maps. We are finally moving into an era of truly accountable, evidence-based artificial intelligence in our hospitals. So I'll leave you with this provocative thought to consider based on the incredible architecture we've explored today. Will AI ever truly replace a doctor's intuition? Or has EviScreen just taken the first major step in finally teaching AI how to think exactly like one? Thanks for joining me on this explainer. I really hope this helped clear up the mechanics behind this groundbreaking research. Keep learning, and I'll catch you next time.